Professor Brown here, and in this video we are going to discuss the periodic table and talk about how we can identify some periodic properties of our chemical elements and classify some of them into families based on how they react with other elements. Here in this picture, we can see a periodic table that's been labeled with the families or groups that chemists have identified in the periodic table. The columns that you see labeled here in the main groups, the first column of elements are called the alkaline metals. So everything in group 1 down there is referred to as an alkaline metal. Group 2 is called the alkaline earth metals. The big block in between the two main groups are what are known as the transition metals. Group 13 and group 14 don't really have a common name, but the group that includes nitrogen, the entire group are called nitrogens. In group 16 we have the chalcogens, and in group 17 these are called the halogens. Everything in group 18 is called the noble gases. Chemists have identified these as families of elements because they tend to undergo the same types of reactions with other elements. For instance, sodium and potassium both combine with chlorine in a 1-to-1 ratio, where magnesium and calcium in group 2 combine with calcium in a 1-to-2 ratio. Chemists noticed this periodicity of the reaction types of the different elements and arranged them into the periodic table first based on that reactivity. And we see that we don't really have individual columns in the transition metals or in the lanthanides or the actinides, which are the F orbital elements down here in the bottom. Those, since they have the F and the D orbitals, they don't display quite the same patterns of reactivity that the other elements do in the so-called main groups. And so the main groups of elements are the ones with the common names, the common family names that have been known for a long time. It took a good deal more study to understand the chemistry of the transition metals and the lanthanides and actinides, so that hasn't been understood for as long as the main group elements. The reason for the similar reactivity that we recognize from the periodic table is due to each group or family having the same number of valence electrons, and that is the number of electrons in the highest principal energy level for quantum number n. We see that everything in the group 1 family, the alkali metals, they all have one valence electron, and that's why they tend to react the same way all the way down the group. Here in group 2, the alkaline earth metals, all of those will have 2 valence electrons, so they will have 2 electrons in their highest energy level. Everything in group 3 has 3 electrons, 4, 5, 6, 7, and mostly 8 all the way on the other side in the periodic table down the noble gases. So we also see a note here, if you remember the discussion of electron configurations, the transition metals will have 2 valence electrons, so their highest principal energy level by necessity will have 2 electrons in the s orbital. However, they will also have some electrons in the d orbital just underneath that s orbital, and those can tend to react as well, and that's why we don't see the same patterns bear out for the transition metals like we do the main group elements that aren't using their d orbital electrons to react. So with that understanding, we can glean a few periodic trends from our periodic table. As we just discussed, it was known before the understanding of electronic structure that the characteristics and reactivity of elements seem to be periodic or repetitious. We now know that that can be attributed to the repeating patterns of electron configurations. There are some other characteristics and behaviors of atoms that display this repetition as well, and sometimes it is also related to the number of protons and neutrons in the nucleus. And we are going to discuss 3 of those periodic trends here, talk about what each of those trends represents and the direction of that trend on the periodic table so that we can use those trends to make predictions about the characteristics that we will discuss. So the first characteristic that we are going to talk about is atomic size. And we can see atomic size, the way they define atomic size is they take the distance between two identical atoms. Think oxygen or something, O2. So they take an O2 molecule and they measure the distance between the two nuclei if they were joined by a covalent electron sharing bond. The reason they do this is because, as we've discussed, electrons are now thought of as these clouds of probability, so actually defining the edge of the atom is kind of tough. So instead, we define their size or their radius by half the distance between nucleuses when they're bonded together with the exact same atom. Atomic size, as you may expect, increases as you go down the periodic table because you're adding electrons to the atom. And for every new row that you move down the periodic table, if you look at the electron configurations, every new row means you're moving to the next energy level, the next highest energy level. So the distance from the nucleus is growing bigger. So going down the periodic table increases the size of the atom. However, going across the periodic table from left to right decreases the size of the atoms. And that may not be what you expect, because we know that we are adding electrons as we move from left to right across a row in a periodic table. However, you have to consider that we are also adding protons to the nucleus when we make that left to right nucleus. Since we're adding protons to the nucleus and we're adding electrons to the same energy level as we move across a row, the greater positive charge by the addition of those protons squeezes that energy level in tighter and actually decreases the size of the atom. This is what is known as effective nuclear charge. That positive charge in the protons pulls the electrons closer as you add more. And so as you go across the row of a periodic table and you're adding electrons into the same distance energy level, the protons start to pull that in, making it so that as you go across the row of a periodic table, the size actually decreases. We can see that trend here laid out in a periodic table, and we will see that atomic size increases as we go from top to bottom on the periodic table, and it also increases as we move from right to left. Again, it's probably easy to understand why it would increase in size moving from top to bottom. It may be a little bit less intuitive why would it increase from right to left instead of left to right, but we've had that discussion just here and now. The next behavior or characteristic that we are going to discuss trends on in the periodic table is something known as ionization energy. So ionization energy is the amount of energy required to remove the most loosely bound atom from an atom in the ground state. So the electron kind of out there, the easiest to remove valence electron in an atom, how much energy does it take to pick that electron off? This trend generally decreases going down groups because valence electrons are further away from the protons in the nucleus. So when we have a big atom down near the bottom of the periodic table, its valence electrons are way, way, way away from the nucleus, and they're not attracted very hard by that positive charge. So it takes less energy to pull that electron away. Versus electrons on atoms that are like fluorine or oxygen, those electrons, the valence electrons, are really close to the nucleus because we are only on principal energy level 2. So it takes a lot more energy to pull those away from those protons. There's a lot of attraction there. This generally increases going across the periodic table, unlike atomic size, because of that proton count. More positive charge holds those electrons harder, so more energy is required to remove electrons with more protons. All of the ionization energies are a positive value reported in kilojoules per mole. So this is an actual measured quantity, and we measure how much energy is required to remove 1 mole of electrons from 1 mole of these atoms, and that amount of energy in kilojoules is how much we report, kilojoules per mole. All of these are positive. Positive means this is an endothermic process. Energy is always required to remove an electron from an atom. You will never receive energy from this process. It always costs energy to remove an electron from an atom, and so this is known as an endothermic process. And the kilojoules, the energy values are positive, meaning the energy had to be used for the process to take place. Here is the ionization energies, the first ionization energies of some selected elements, and we can see the trends laid out in arrows here. We can see that the amount of energy required to remove an electron increases as we move across a row. There are a few exceptions in there for various reasons, but not many. It also increases, it's easier to remove electrons from the bottom elements than it is from the top elements, because those electrons are held so close to the nucleus. Our final behavior and characteristic that we are going to discuss are the electron affinities. And in a way, this is the reverse of the electron ionization. The electron affinity describes the energy change associated with adding an electron to an atom in the ground state. So how much energy change is required to make a negative ion from any atom? This process can be endothermic for some atoms. It can cost energy to put electrons in some atoms. It can be exothermic for others. So sometimes adding an atom increases the stability of, or adding an electron increases the stability and will actually give us some energy back from the process. Instead of that electron wants to be there, it will slot into that and give us energy back instead of requiring energy to be placed in. Sometimes this energy is required, sometimes the energy is released, in other words. Positive means energy has to be input. It is endothermic. Negative means energy is released. A negative value means this is an exothermic process, and we get energy back from putting the electron on this particular atom. And just as the ionization energies were reported as kilojoules per mole, this is also reported in kilojoules per mole. So it's the unit is reporting how much energy is required to add 1 mole of electrons to 1 mole of some ground state atom. If we look at the trends for the electron affinities, we can see that it is very close to the same trends as the ionization energies, with a few exceptions, and I want to talk about those exceptions here. So we can see that the group 1 elements typically give us energy back when we add an electron to those atoms. And the reason is because all of these have a half-filled s orbital. They only have 1 electron in their valence s orbital. When you add 1 electron to it, it fills the s orbital, and that is a very stable configuration. And so adding electrons to these atoms is an exothermic, stabilizing, energy-releasing process. Group 2 is different. Group 2 has a bunch of positive numbers because they already have a full s orbital. And to add an electron to any of these atoms, you must move into the p orbital on that particular electron shell. And to move into the p orbital costs some energy. So all of these have positive endothermic, energy requiring processes of adding an electron to this atom. Then we can see that it resets, and we get some stabilizing factors by, once we're already in the p orbitals, it starts to increase again. We get more negative values here going across the rows, which means that we get more energy back from adding an electron from boron. We get more energy from adding an electron to carbon. Then we do run into another exception here at row 15, or column 15 rather. And the reason is all of the atoms in group 15, column 15, family 15, the nitrogens, already have 3 electrons in their p orbitals, meaning their p orbitals are half full. And so to add an electron to that p orbital, some of it in nitrogen, it's almost a balanced process. In the rest of them, it doesn't cost energy, but you don't get as much energy back from the previous row. And so the reason for that is because that p orbital was half full. And then the trend increases again for the next 2. We like to add electrons to oxygen. Fluorine, chlorine, and bromine, and iodine love to have electrons added to them. However, we might remember that the noble gases have a full s and p orbital. So to add an electron to any of the noble gases is going to require energy. So for the electron affinity values, the amount of energy associated with adding an electron to an atom, we have a general trend of increasing from left to right across the periodic table, with a few noted exceptions here. And we have a general trend from bottom to top. It's easier to add electrons to smaller atoms than it is the larger atoms, because it's easier to get those attractions to the protons going. That is the end of the discussion of the periodic table. There is an auxiliary video to this one where we go over some of the problems that could be answered using the topics we talked about here. Please check that out for more information on how to complete those exercises.